Good evening, mga Bisaya. So I got this question a while ago. In fact, I already posted about it, but I've been receiving questions about how to do steel connection. So I will just discuss all together. So basically, this question he was asking um, how to design. He said how to design the connection if there are no forces divided or forces provided, and it only said in the plan that this one where there is no moment is indicated where no moment is indicated in the drawing, provide full moment capacity of member zero point 0.9 if y z, and where no vertical shear indicated in drawing provides full shear capacity of 0.54 if y dtw. So basically, when I first read this question, I know exactly this where this project location is. I asked him, like, is this in the US or Canada? Because this is really common here. Like all connection design, um, it's or not all, but especially for larger projects, most engineer here will delegate the design of the connection to a specialty engineer. Um, Most of the time, whoever did the um, shop drawing is basically the one who will do the connection design as well. And they will hire a different engineer just to do the connection design and then detail. Um, in my practice here, well, at first I was also surprised with that setup before, but every time I have a steel building design, I always do the calculation of the connection itself. Like I don't delegate it. But this one, what I noticed is it says if there's no moment provided or indicated in the drawing, it will be designed for the full plastic moment capacity, which is if this is the typical call out in the drawing that all connections will be designed based on this plastic moment, it's gonna be really expensive because if you design everything to the full capacity, like for example, if you have so for example you have a this is a column and then this is your beam, right? And then you will have a usual like stiffener here, and then the the in shape like stiffener, and then you will have the movement plate right here. That would be your movement plate. If this is welded or bolted, right? That's bolted, and then you will have your shear plate here. And then, so if this connection is designed by or based on the full plastic moment capacity of the building, it's gonna be really expensive. And I don't typically do that when I do a like I will determine the whatever's the actual um demand, then I will design based on that one. But most of the time, what I will do is I will have some kind of a table, like the same with this one here. So, like for the shear, I will use the actual or whatever's the required shear, and then sometimes, I will add like maybe 25% of the demand. And what I usually do is I will, instead of designing a connection for each member, what I will do is I will have some kind of a table. mm, I will have some kind of a table, and then I will have the section here, and then I will group them together. Like for example, for all W16, all W18, all W. um, 21, and then all W24, something like that one. And then I will have some kind of like share plate, like share plate size. Then I will have the size here, and then moment plate if required, moment plate size, and then number of bolts. So share plate and number of bolts, and then share plate, number of bolts, something like that one. So I will have a table, and then I will group all together W16, and then I will determine whatever is the maximum applied load for the old W16, and then I will, you design everything based on the maximum, then W18. And sometimes if these two are the same, or the range of the load, or the applied load intersects, then I will group this together like W16 and W18, something like that. So you get the point. So instead of, like I said, instead of designing this one, now what I've noticed in like what I've seen in Facebook, most of the time the connections are done by, or they use like a software to do the design. The what's that? Statica, and I'm not really familiar with that one. I will, like, all my design, like connection designs until now, it's I'm, st- I'm still old school, so I will do it by hand, just using the table. And it's not really that complicated. Once you have the um, easy design manual, there's a load table there, then you can use it. So let's try. Um, let's do a quick example. So this one, I just copy, pasted this one from the EIEC design manual. I think 13th. It's an old one. So I don't know if in the new edition what's the difference, but I mean you'll get the idea of how to do the design. So I would assume the table is still the same. Maybe there's a slight increase or decrease in capacities, but the steps or procedure will still be the same. So for example, we will have a um, what's the section? What table did I use here? W40, 36, 30, 27, 24. So we'll just use 24 because this table here includes W24. So say W24 by uh, 94 for sake of discussion. So we will use W W24 by 94, and the information you need is the well, of course, the what we call this one, the uh what supports this one. And usually we'll use W14 for columns, because this is the, I would say, most common column section, W14. So this is our beam, and then we'll use for the column W14 by um, say 99, W14 by 99. So this is our column. And the information you need for that one is, well, of course, if this is a moment connection, you have to make sure that the flange of the column, that's why we typically use W14, because the like for most W14 sections, the flange width, the beam, the depth is almost the same as the flange width, and it's wide. So if it's a moment connection, then like you will have wider, you know. So if this is your This is your column, and then your beam is right here. So you just have to make sure that this flange, the column flange, is wider than the steel beam. But if it is just pure shear connection, then it doesn't really matter. So the information you need for the beam is you need the web, no thickness of web for W24 is W24 by 94. Thickness of web is 0.515 inch. And then for W column, W14 column, the thickness, you need the thickness of flange because the connection will be the web, the beam web through the column flange. So that's why you need information for the thickness of the web of the beam, and then thickness of flange for the column, which is W14 by 99. Thickness of flange is 0.78. This is 0.78 inch. So these are the information you need for this section. So basically, um, our connection would be, let's try another right here. So beam is W24 by 94, and then column is W14 by 99. And then for beam thickness of web is 0.515, and then column thickness of flange is 0.78 inch. So our connection would be, or detail would be, this is the column, right? So if that's the column, and then this is the beam right here. And then the connection you need is now this one, the table that is all bolted double angle. So that is all bolted double angle. So this is your angle here, like that. So it will be bolted here and then bolted also right there. So this is a shear connection. Now, for, for example, the load, say, um, shear did is just for the sake of discussion, say this is 25. I will be using a like imperial because the table I have is in imperial. So, I mean, if this is metric, the procedure will still be the same. So, say for example, lead load is 25 kips, and then shear for live load is a 40. For the sake of discussion. So this is 40 kips. So therefore, our factored load, you know, factored shear would be 1.2 times 25 plus 1.6 times 40. That would be 1.25 times 25 plus 1.6 times 40. This is 95.25 kips. So that is your factored. And then the service would be 25 plus 40 is equal to 65 each. So we have now these design values. Now the reason I have this factored, like both the factored and the service load, because the table um is includes like also includes ASD and the LRFD values. So first is so we have the factored load 95. So all you have to do is from the table, say for example you have how many bolts are there? One, two, three, four, five, six. So you there in this table here, there are six bolts. All you have to do really is determine the number of bolts based on your section. Make sure that it will fit. It will fit your beam depth. And usually, this table shows like these six bolts will fit between W21 and W40. So you can have that um, number of bolts. So it depends on the capacity, but for the sake of discussion, we'll just use this table here. In the actual manual, you will see a lot of tables depending on like the bolt diameter, this one, and then what this here, six rows, and then six rows will fit between W21 and W40, and then our WB at our beam is W24, which is this one here. So we are good. So we will use six bolts. And now all you have to do is say your you will use a an angle of 5/16. So these are the available thickness of your angle, and then it has different capacity based on the thickness of the angle because in connection design you will check everything like tearing of plates, bearing, um, both the angle and the um, beam web. So all you have to do first is you select the thickness. It's either you go with 5/16 or 3/8 of an inch. And usually when I design a an angle connection, I will typically use the 3/8 thick um, angle. Now, if you noticed, the capacity of a 3/8 angle and one half inch angle is the same. See, you notice this one, 191. This is also 191. So there's really no point of going half inch thick because you don't gain any um, extra capacity. What this means is what governs the calculation is not the angle itself. It is the beam web. So from here, you will see, so we'll use, say, like I said, we will use 3/8. This is my favorite section or thickness. So if you notice, you have your thread condition, you have your N and your X. So N meaning the thread is included in the shear plane. So for example, if you see a bolt, so if this is your bolt, some bolts have um, thread only right here in this section only, and then there is a solid portion here. Now there are also bolts that basically the thread extends all the way here. Now what the N means, this in, which is the thread is included in the shear plane, that means your, so for example right here, so that's your bolt with threads right here only, so like that. So that means your shear plane is right here. So this could probably your thickness of your plate, the thickness of the angle and the web, including the web. Um, if you add the thickness, it will be right here. So this is your shear plane right here. Now, if your plate is thin and your share plane is right here, then you will use the value of x. But the rule of thumb in designing a connection, unless you yourself select, or specify the actual bolt length, it's always safer to just use the n value, because that's the smaller between the two. So if you imagine, if this is if the share plane is excluded, then it has a capacity of 224 kips versus 191. So what if you will use this value, like the x capacity, and then in the actual, the the bolt, or the share plane is within the threaded part. So that significantly reduce the capacity. So that's why it's always safer to use the in value. So in this particular example, so we will use n, that meaning the thread is included in the shear plane, and then 3/8 inch thick angle. Then we will use first the LRFD. That means our capacity is 191. So based on, let's just say, based on table, whatever table, the um, shear resisting, right, is equal to 191 kips, which is greater than this one. So this is okay. Now the ASD, so this is 65. The capacity based on ASD, the allowable stress design, is what? 127. Then compare that to this one, which is 65. So this is LRFD, and resisting based on ASD is equal to 127, which is greater than 65. So therefore, your connection is okay. Now, there's one more check, or two more actually. So this is already based on the bolt capacity. Now, you will check this one here, the beam web available strength per inch. This one. So that's why we need to get the thickness of the web, because this one, it will calculate um the so for example, um you have two options, or two values here. You have the cope, or three. You have the cope at top flange only, the cope at both flanges. These two options are basically applicable if you have a beam to beam connection, where you have, you know, where you have the, if this is your girder, and then you need a beam right here. Your beam is right there. Then you will connect this one. So this is cope at top flange only. That is applicable if this girder is really deep versus the depth of this one. Then you need top flange only cooped, or if the depth is almost the same, then you need coop also at the bottom flange. Now the capacity on that one, depends on the situation of your connection. Now, if you remember, our connection is from a column, or from a beam to a column. Therefore, you don't need a coop here. In some cases, you will need a coop at the bottom flange. But um, so if in this connection we will use the table for the uncooped, this one uncooped section, because you don't need the beam to be cooped on that one. Now, this depends also. This, we have the standard hole, we have the oversized hole and then the short slotted hole. And then you also have to determine what's the LEH. Now in the table, the LEH is um, this one. Uh, if you so we will do the connection. So if this is your beam, right? And then this is your angle connection. That LEH is, if you look at the table, I don't know if it is clear. That's the distance between the end of the beam to the bolt line. This one, so if your bolt is right here, this is only critical if you have a cope, cope flange, but for uncooped flanges, it's just, I mean, you will have, if you notice here, the capacity is still, or, you know, if you notice the capacity, so 351, 351, 351, 351, 351 for ESD, and then the LR is 526, 526, 526. It doesn't really matter if the section is uncooked. Now, with regards to the so that's your LEH, this one. So this is your LEH. And then your LAV is if it is cooked. So for example, this section is cooked right here. So this is your LAV. I mean, in the table, you will see in the table here, um, there is a sketch, with all the information you need. So all you have to do is select, say, for example, the LAH, the most common is half one and one half, and the same as or it depends on the LAV, whatever is the final or the actual, what do you call this one, based on when you cook the flans, because it depends on what's the key value. So if this is your beam section, remember this one is not really at an angle like 90 degrees. There's a curve here, and then you have to clear this curve, and this is the key, because this one is the key one, and then this is the key value. So you have to check this one, what is this one, and then that will be your minimum clearance from the top flange. But our section or our connection is uncooked, so all you have to do is basically use this table. So regardless of what's the LEH, this one, whatever is this value, it's the same. So therefore, our capacity is 526. So 526. So checking the beam web, no, check the beam web for bolt bearing. The capacity is equal to um the capacity is what's this one? 526. The capacity is 526. That is per inch. This is 526. Oh, 526 keeps per inch of the web, but our web is what thickness of the web is 0.515. So therefore, your Rn is 526 times 0.515. Our capacity is 526 times 0.515. This is 270.89. And then next check is the next and the last one would be uh the what do you call this one? The bolt bearing on the column flange. Now, if you look at the table, this one, um, support available strength per inch thickness keeps per inch for for the flange is 1050. So for column flange, mm, so this is for beam web. So you have to check column flange for bolt bearing. Capacity is equal to 1050 times what's the flange thickness? It is 0.78. 0.78. So this is equal to 819. So that's, I mean, what, 300% higher than the web. So all you have to do is determine the minimum of all the capacity. So you have the capacity is 191, 191, and then 270. So is equal to 191, and there's 270, and then the last one would be 819. So therefore, your connection 6 volts, so 3 inch thick angle with 6 volts, your final capacity is 191 kips, which is still higher than the applied load, which is 95. So that's it. I mean, that's how you check the capacity of the connection. So as long as you have the table, you don't really need any, software a bit. The old way of calculating that one is by hand. So you have the table. I mean, it would be nice if you can do it. I don't know how to use the Statica. I think once you're familiar with the procedure, it doesn't really take too long to calculate the connection. All you have to do is get the reaction, determine the parameters, thickness of the web of the beam, and thickness of the flange of the supporting. Um if the supporting element is a beam also, then this instead of thickness of the flange, then use the thickness of the web. So it's the same. And what else? So that's it for the bolted connection. Now for the welded connection, um, it follows the same procedure, except you will calculate the thickness of the web. Now this one, you have two weld types, weld A and then weld B. The weld B is for the supported beam, and then weld A is the welding to the support member. So in our connection, we have the weld A is for the weld uh, design for the column. So this is weld A, and then for the beam is weld B. Now the check, all you have to do is, now for this one, you already know that you would need, or not really. I mean, you can determine, or you can have the angle, um, you know, not the same as the length of angle required for a bolted connection, because you don't have to um, uh, meet the bolt requirements. But if you will use the same, this one is what, uh, 15, 15 plus LEV. So all you have to do for bolted is you will select so our beam depth is 24, and then minus whatever is the key value. So it would be safe to assume, you know, either use W or length of angle 18 or 20. So for the sake of discussion, we'll just use um, 18. So that's the length of the angle. Now you are checking the capacity or the weld connection to the beam web. So that is weld B, this one. So if you have the weld B, now the weld size, you have to make sure that I think the your thickness of weld, no, the weld should be greater than or should be less than uh, no thickness of say web. Is it 1/16 thicker? So the thickness of the web should be greater than the thickness of weld plus 1/16, I think. So for sake of discussion, we will use the same angle, which is 3A. So your maximum thickness or maximum weld size would be 3/8 minus 1/16. That would be 5/16. So 5/16, this is your weld size, this one. So with that, you already have the capacity of 196. This one, 196, right? And then you will have the minimum web thickness, which is 0.238 for that um, uh, to get the capacity of 196. Other than meeting the weld requirements, you also need to make sure that this web thickness, that's the minimum web thickness, is thicker than the web. So our web thickness of web is 0.515. So that means that is greater than 0.238, which is the minimum. And that is okay. So that's how you determine the thickness of the um, what do you call this one? Not thickness, the capacity of the connection. And what check do you have to do? Um, I think that's it. So all you have to do really is, you know, so when you do the detail, you have to make sure that you meet all these assumptions that you use in the design. You have to have a length of 18. The thickness, the size of the wheel is should be 5/16, and then we already know that the thickness of web is greater than the minimum thickness here required. So in that uh, in that regards, we are okay with our connection, and our capacity is 196, which is greater than 95. So if you notice, the capacity is way much higher than the demand. So instead of using the 18, like the length of the angle, then you can significantly reduce this one, maybe 16 or 14, whatever is the length required. But there is a minimum depth or minimum length of the angle for stability requirements. If I remember correctly, it should be at least half the beam depth, I think. But yeah, if you have the manual, you can read about it. And yeah, all you have to do is basically just like compare, with this length, thick size of the wheel, this is capacity, and make sure the thickness of the web is thicker than whatever is the specified minimum web thickness here, and that's it. And the same procedure with the what we call this one, the welding to the support, like the column flange. Um, there are in some cases you have to do like extra connection check. For example, if you are doing a connection to the HSS, so you have to make sure that the HSS, the hollow steel section, meets the minimum thickness required also for the welding. So the, I mean, like I said, once you have the manual, um, and then by the way, the manual has a companion like um, design example. So each manual has a design example also. So you just follow whatever is in the manual and in the design example. So it's not really that complicated. Now the same with if you have a single plate connection. So instead of the usual double angle, if you have a, for example, this is your column. If this is your column and then you have your beam here, so that's your beam, then you will sometimes you will use a single shear connection, single shear plate like that instead of the usual, double angle. You will just use single shear plate. So the manual has also a load table for that one. And in this calculation, in this scenario, this bolt calculation here, you will follow the same procedure as if, that's the bolted angle. All you have to do is check the, um, you will see this one here. So L, for example, L is, this is also the number of bolts. All you have to do is check. Now we use what in the angle, double angle is when we use um, 6 bolts and then included, right? Oh, thread is included in the shear plane and then the standard. And then all you have to do is, select the plate size. Say our plate thickness is 3/8 and then LRFD. So our capacity is, where is the 3/8? This one. So therefore our capacity is 95.4. So almost the same as the angle here. Is it this? Oh no, 190, 191. Now, if you notice, the connection is, um, I think what happened here is, so if you notice 191 versus 95, the same number of bolts, it is the probably because in double angle you have double shear, right? But for single plate connection, you have only single shear. That's the, so for example, this is your web, right? This is your web. For single plate, this is your shear plane. But for double angle, you have another shear plane here. So maybe in this calculation, what govern is the shear of the bolt. So that's why in double angle the capacity is 191, but in single shear, single plate is always also only 95. And then our demand is also 95. So I will not, I mean, I won't be comfortable having a capacity the same as, you have to have some kind of, extra like allowance. So if it was me, the capacity for 6 bolts is only 95. I will increase the number of bolts. So you need 20. Now, for some reason, if this 7 bolts, which requires a 20 and a half length of plate, and then it will not fit inside the beam web because you have the thickness of the flange and then you have the fillet here. So this one, this is your clear distance. This is key. This is also key. So basically your allowable length is equal to d minus 2k. So this is your allowable length. Now, if this allowable length is less than this one, then you are limited to the number of balls, which is 6 only. And then your capacity is only 95.4. If and then your actual load is 95, so you only have like 400 pounds extra. So if that's the case, you have no other option but to go with double angle instead of just single angle. So that's what if you use double angle, you will have a positive 191. So for example, for the sake of discussion, our demand is only like 70 kips, and then our capacity is 95.4. Then this is okay. Use 6 bolts in, and then the wheel size would be, this is the recommended wheel size, because if that's a single plate, you know, that's a single plate. The connection here should be welded. I mean, there's no way you can bolt at one. So it has to be a welded connection. So if that's the case, your minimum wheel size should be 1/4. So you just have to, you know, look at this. I don't have the sketch. In the manual, there's a sketch there, like where the wheel is required. And so that's the wheel size. And that's it. So that's how you determine the connection, number of bolt, size of plates. Because like here, if you use single plate, even if you increase the thickness of the plate, doesn't really matter. Even with unless here. So if you are if you are to use the single shear plate, if you noticed here, for the shear plane excluded, the capacity is 116. So you can still, like, based on this one, you can still use the single shear plate, but it has to be like the shear plane has to be excluded from the thread has to be excluded, or the shear plane has to be excluded from the shear plane. So it's more of a quality control now. Like, you have to make sure that the bolts, when they submit a shaft drawing, the bolts, like you have enough room. uh, It's not threaded all the way to the head. So it should be, if you will use the threaded or the excluded value, then you just have to make sure that when they submit the shaft drawing, if this is the, so you have a washer here, right? So you have a washer, and then you have the shear plate thickness, and then you have the width. You just have to make sure that this shear plane here, this shear plane is not located in the thread portion. So usually the thread is right here, so you can put your knot. So as long as this is the case, then you can use this value. So anyway, um, I think that's it for today, and we'll see what other questions we'll get. But yeah, as long as you have the table, it's not really that difficult. Well, if you have the software like the Statica, then it doesn't matter also. I mean, as long as you're comfortable using it, then that's fine. So anyway, uh, till next time. Okay.